Hello everyone, I welcome you to this lecture of soft computing techniques. This is the fifth lecture of module 4. Till now, we have covered basic concepts of genetic algorithm and some encoding techniques of genetic algorithms. So, we have learned some encoding and decoding techniques. Basically, this is known as the actual solution space. Actual solution space. And this is known as computation space. So from actual solution space to computation space, this is known as encoding. And from computation space to actual solution space, this is known as decoding. So the actual solution space is known as phenotype, and the computation space is known as genotype. So you can say the genotype is the population in computation space and phenotype is the population in the actual real world solution space. So we have studied different encoding technique like binary encoding, real encoding, foundation encoding, etc. So there are two more encoding technique. What is that? Octal encoding. So you know the octal numbers, it is 0 to 7. So the octal encoding, so in the octal encoding, we use a string made up to octal number from 0 to 7. Suppose the chromosome 1 is 1, 2, 3, 4, 5, 6, 7, 0. So the value of these things 1, 2, 3, 4, 5, 6, 7, 0. So that is basically you can write 0, this is 1, 2, 3, 4, 5, 6, 7. So this number is equal to the this number 1, 2, 3, 4 is equal to 1 into 8 to the power 7 plus 2 into 8 to the power 6 plus 3 into 8 to the power 5 plus 4 into 8 to the power 4 plus 5 into 8 to the power 3 plus 6 into 8 to the power 2 plus 7 into 8 to the power 1 plus 0 into 8 to the power 0. So this is basically the octal encoding. So from the this number you can find the real number. Another thing is that which is known as the hexadecimal encoding. So here hexadecimal is the we will use the number from 0 to 9. So 0 we use this number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So in octal encoding we'll use a number from 0 to 9, that is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and the alphabets A means 10, B means 11, C means 12, D means 13, E means 14, F means 15. So if the number is D, A, 1, 4, 3, so that is basically 10, this is basically 13. So number is 13 into 16 to the power 0, 1, 2, 3, 4. So 16 to the power 4 plus 10 into 16 to the power 3 plus 1 into 16 to the power 2 plus 4 into 16 to the power 1 plus 3 into 16 to the power 0. So in this way we can uh, decode the octal numbers. So we have studied the binary encoding, real encoding, and the foundation encoding, etc. So now try to understand. So now try to understand the comparison between these uh, encoding techniques. So the most common method of encoding, which is the binary encoding. So most common method of encoding, first is binary encoding. So binary encoding is one of the most frequently used methods for representing solution in optimization problems, particularly when the search space is discrete, that is finite set of populace, that is finite set of possible solutions. In binary encoding, a solution is represented by a string of binary digit from that is 0 and 1s. So each bit corresponds to a variable or decision in the problem, and together these bits represent a complete solution. Representing a gene in terms of bits, that is 0 and 1s. So each individual solution is represented as a string of bits. For example, 1 0 1 0 1 0 0 1. Here each bit in the string may represent a different decision or parameter of the solutions. In an abstract problem, each bit could represent whether or not an item is selected. So for 1 means selected or 0 means not selected. So suitability for discrete search space. So optimization in a discrete search space refers to problems where the solutions are distinct and finite. Binary encoding is a particularly well suited for each problems because the search space can be represented as a set of binary strings where each unique combination of bits corresponds to a potential solution. Binary encoding allows for efficient use of genetic operations such as crossover and mutation, which can be applied directly to the binary string. So crossover mutations are easy in binary encoding. It is especially effective for problems like combinatorial optimization problem, traveling salesmen, job scheduling, or knapsack problems. Discrete variable optimization, where each bit can be treated as a discrete decision variable. So benefits of binary encoding. First one is efficiency. It provides a compact and efficient representation for large solution spaces. This is easy to manipulate. Operation like crossover, that combination of two parent strings, and mutation, randomly flipping bits, can be easily applied to binary strings. Clear mapping to discrete spaces. Since many optimization problems inherently involve discrete decisions, binary encoding naturally aligns with these types of problems. So some drawbacks of binary encoding. So limited expressiveness. So representing a real example continuous parameters with binary encoding can be inefficient for problems involving continuous spaces. Other encoding like real value encoding may be more appropriate. Fixed length representations. Binary encoding often requires that the length of the binary strings be fixed. Each can lead to inefficiency if the solution space does not need that many bits. In summary, binary encoding is particularly effective in optimization problems with discrete solution spaces, providing an efficient and clear way to represent solutions for genetic algorithms. The second encoding technique, that is value encoding. So value encoding is another method used in genetic algorithm and optimization problems. It differs from binary encoding in how it represents a solution or gene, where a breakdown of the key characteristics. So first one is that represent a gene as some value. In value encoding, a gene is represented by a direct value as opposite to binary strings, that is binary encoding. These values could be integer, real numbers, characters, or even more complex objects depending on the problem being solved. For example, if the problem involves finding the optimal set of parameters, each gene might directly represent one of the parameters with a value from a predefined range, as for example integer or floating point numbers. Types of values. Integer, in case where the problem involves selecting discrete numbers or quantities, an integer might represent a gene. Real numbers, for problems involving continuous variable like optimization of real valued functions, genes can be real numbers, that is floating point numbers. Characters. In certain cases, a character or string might be used to represent a solution, as for example, solving problems involving strings like DNA sequence matching. Objects. For more complex problems, seen can be entire objects or structure, such as matrices, lists, etc., where each object represents a complex feature of the solutions. Third one is the direct representation of variables, that is design parameters. In contrast to binary encoding, the value encoding directly maps the design parameters or variable in the problems to other values. For instance, if optimization a set of parameters like x and y in a function fxy, the gene could simply be represented as a tuple of numbers, that is x 2.5 y 7.3. So if you like that, 2.5, 7.3, these are the genes, but this whole thing you can write a chromosome. So whole thing you can write a chromosome. This allows the genetic algorithm to work directly with the values of the parameters, avoiding any need for intermediate steps like binary to decimal conversion, which binary encoding often required. Avoid intermediate encoding and decoding steps, so no need for conversation. With value encoding, the solution is represented directly, so other no need for the additional encoding and decoding steps, as for example converting a binary strings to real number or decoding a binary string into the item selections. This simplifies the genetic operations, since you can directly manipulate values without having to deal with intermediate representations converted black converted back and forth between binary, integer and real values. This is most suitable for optimization in a continuous search space. So continuous search space involve problems where the solution variable can take a range of real values rather than discrete choices. For example, optimization problems involving real numbers variables, such as finding the minimum of a function or adjusting parameters in machine learning, often benefit from value encoding. In this problem, genes are often continuous real numbers, and value encoding provides a natural way to represent them. Problems where binary encoding may be cumbersome, that is, requiring many binary digits to represent precise real numbers, are well suited to value encoding. Some benefits of value encoding, so that is simpler representations. There is no need for complex binary to value conversion, as the solution directly corresponds to the parameters of the problem. Efficiency in continuous optimizations. When dealing with real number or continuous optimization problems, value encoding allows the algorithm to work directly with values without approximations or intermediate conversions. Better for real world variables. Many real world problems involve continuous variables, as for example optimization design parameters, control systems, or machine learning hyperparameters, where value encoding fits naturally. Some drawback of value encoding: it is potential for slower convergence. In some cases, especially in continuous optimization, value encoding can lead to slower convergence to the global optimum compared to other encoding methods, particularly if the problem space is complex and highly multidimensional. Crossover and mutation challenges. While crossover and mutation operations are straightforward with binary encoding, they can be more complex when dealing with real value or structured genes. For example, combining two real numbers might require interpolation or blending, which can be tricky. Difficulty with discrete variables. For optimization problems that involve discrete choices, such as the knapsack problem or traveling salesman problem, value encoding is less efficiency than binary encoding. The third one is that permutation or order encoding. So permutation or order encoding is a method used in genetic algorithms where each chromosome or individual represents a sequence of elements. This encoding technique is specially suited for ordering problems where the goal is to find an optimal arrangement for or sequence of items. Some key characteristics of permutation encoding. So chromosome represents a sequence, that is order of elements. So in permutation encoding, Each chromosome is a sequence that represents a particularly ordering of a set of elements. Unlike other encoding that represents individual values, the elements in permutation encoding are placed in a specific order. Each position in the chromosome corresponds to a specific element, and the order of elements in the chromosome matters as it directly represents the solution. For example, if the problem involves arranging cities in a specific order for a traveling salesman problem, the chromosome might look like this, that is from city 1 to city 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 7 to 8, etc. So, second is that used in ordering problems. Permutation encoding is particularly useful in problems where the order of elements is important, such as traveling salesman's problem. As you have seen, the goal is to find an optimal sequence of cities to minimize travel distance or maybe the minimize the traveling cost. Job scheduling, the goal is to find the optimal order in which jobs should be processed to minimize completion time. Vehicle routing problems, similar to TSP but involves routing multiple vehicles. Flows of scheduling, the goal is to determine the best sequence jobs through a set of machines to minimize processing time or maximize efficiency. Some benefits of binary encoding. So natural representation for ordering problems. So permutation encoding is a natural way to represent problems where the order or sequence of elements is crucial, such as TSP or scheduling problems. Direct manipulation of sequence. Since the chromosome directly represents a sequence of elements, it simplifies the genetic algorithm's ability to evaluate and manipulate the order of elements. Effective for combinatorial optimizations. Many combinatorial optimizations like TSP can be efficiently tackled using permutation encoding. The challenging of permutation encoding. So valid permutation. So ensure that crossover and mutation operations produce valid permutation. That is no repeated elements. So it can be more challenging than other encoding like binary encoding. Special care is needed to maintain the validity of the chromosome. Such as, for example, suppose there is chromosome 1, this is 1, 2, 3, 4, 5, 6, 7, 8. If I write a chromosome 2, that is 8, 7, 6, 5, 4, 3, 2, 1. Now do a 1 point crossover. So offspring 1 can be like that 1, 2, 3, 4, 4, 3, 2, 1. Offspring 2 can be like that 8, 7, 6, 5, 5, 7, 6, 8. So these are not a valid chromosome. So that we need to ensure these things. Complex crossover operations. While mutation in permutation encoding, that is swapping elements, is straightforward, crossover operations are more complex. Specialist crossover technique like order crossover or partially matched crossover are required to ensure the offspring remain valid permutation. So we'll study these things. So now try to understand some example of real encoding and also the binary encoding. Suppose we are writing a problem that is maximize fxy, that is equal to x cube minus x square y plus 2xy plus y cube, where x is less than equal to 10, y is less than equal to suppose 10. So here we can write that one chromosome, that is C1, in real valued encoding. So that is real valued encoding. So we can write C1 suppose 7.5 and C2 maybe 6.2. So this is one chromosome in real value. Chromosome 2 maybe X is 5.7, Y is 9.2. So this is a chromosome 2 like these things. So another example is that, so that will go for binary encoding. So question is that maximize fxy equal to x cube plus 20 by y square minus 10xy. X lies belongs to 0 to 3.1. Y belongs to 0 to 1.5 with an accuracy of 1 decimal is 1 decimal point. So here it can be represented as the number of bits is that, so 2 to the power n minus 1 is greater than b minus a by epsilon, so that is equal to 3.1 minus 1 by 10, so 2 to the power n is greater than or equal to 32, so n equal to 5, so 5 bit required, and here 2 to the power n minus 1 is greater than equal to 1.5 by 1 by 10, so n is equal to 4. To represent x, we need 5 bits, so x may be like this 1 1 1, so this represents x. Its y may be 1 1 1, so it represents y, so together this is a chromosome 1 1 1 1 1 1 1 1. So chromosome 2 you can assume like 1 0 1 0 1 0 1 0 1, so that is chromosome 2. So you can do the crossover and mutation, etc. You can do the crossovers. In this class we have studied a comparative study between different encoding techniques. So we have studied. So in this class we have discussed a comparative study between encoding technique. So question for today's class is that assume any TSP problem and find 5 chromosomes. So these are the references of today's class. Thank you.